So in this example problem, we have a beam that's composed of aluminum, right, and that which has an elastic modulus of 10 megapsi, and we have the bottom of the beam is composed of steel, right, and they're bonded together, right. The section is undergoes a, a bending moment of 10 kip inches about the z-axis. So the z-axis would be here. All right. Determine the stress distribution within the section. So what we're interested in is in how does the stress vary as a function of y. Okay. So through the thickness of the beam, how does it vary? Okay. So to do this problem, we're going to follow this recommended procedure. So the first thing we're going to do is we're going to calculate what is the equivalent width of our beam. Okay. So we're going to modify what the width of the steel member will be. We're then going to calculate the equivalent cross-sectional area, determine the moment of inertia, or sorry, the moment of inertia. Then we'll calculate the stress, and then we'll determine the stress distribution within the composite section. Okay, so let's start off with the equivalent width. All right. All right. So we know that the equivalent width from earlier is just going to be equal to the ratio of our two Young's modulus, E2 over E1, times the width, our composite width. Okay, so our equivalent width, right, is for the more stiff section. So steel is more stiff than aluminum. Our original width was 1 inch. Okay, so and our ratio between our two stiffnesses is 30 mpsi for steel divided by 10 mpsi for aluminum, and then that equivalent width was 1 inch. Our composite width was 1 inch, so our equivalent width would be equal to 3 inches. Okay, so that's the first part done. Okay, our second part is to determine the equivalent centroid of our cross-sectional area. So our equivalent cross-sectional area is going to look like this, right? Where we have a two, so we have a 3-inch section, and we have a 2-inch section here. All right. 1-inch section. So this is 1 inch wide. This is 3 inches wide. This is 2 inches tall, and this is 2 inches tall. All right. So we need to figure out what is our equivalent moment of inertia, our location of our centroid. So our location of our centroid, we can calculate as being equal to the sum of the centroid of our individual areas times our areas divided by the sum of all of our individual areas. So we have two areas, call it A1 and A2. So for A1, the centroid of A1 occurs 1 inch from the bottom, so I'll call that 1 inch. And then the area of A1 is going to be equal to 2 inches times 3 inches, or 6 inches squared. And then for the second area, A2, the centroid of that is going to be at 3 inches. All right, and then the cross-sectional area is going to be 2 inches times 1 inch, or 2 inches squared. And then divide by the total area, which in this case would be 6 inches squared plus 2 inches squared, or 8 inches squared. Okay, so if we multiply all this out, we get 6 inches cubed plus 6 inches cubed divided by 8 inches cubed, which would give us a y bar of 1.5 inches. All right, so that's our our centroid. All right, so our centroid of our section occurs here around 1.5 inches. All right. The reason the centroid is important is we need the centroid in order to calculate the moment of inertia using the parallel axis theorem. Okay, so for parallel axis theorem, you can say that the moment of inertia is equal to 1/12 the base times the height cubed plus the area times the distance to the centroid squared. Okay, so in our case here, all right, we have, all right, so this is going to be about the z-axis here. So we have two areas. We have A1 and A2. So we can calculate IZ for area 1, and we can calculate IZ for area 2. And we can say that IZ would be equal to IZ1 plus IZ2. Okay, so IZ1, what we'll do is 112 times the base times the height cubed. So the base times the height cubed here would be 3 inches times 12 inches. Times 2 inches squared. So 2 inches squared would be, all right, and then the area of it would be 6 inches squared times the distance, which would be 1.5. The distance between the centroid of the area 1, the centroid of area 1 is 1 inch from the bottom. So the difference between that and 1.5 would be half an inch. Okay, so all right. Then for the second moment of inertia, we would get 1/12 times the width of the section, which is just 1 inch, times the height of the section, which is 2 inches squared, plus the area of the area 2, which is 2 inches squared, times the difference in height between, or in length between the centroid of area 2 and area 1. So the centroid of area 2 is at 3 inches, so it would be 1.5 inches from the centroid of area 1. So if we add these two together, we would get IZ. So IZ ends up being 8.667 inches to the fourth. Okay. All right. The last part of the problem, or the next part of the problem, is asking you to calculate the stress distribution within the equivalent section. Okay. So our equivalent, the stress, right, within the equivalent section is equal to minus my over I. Okay, IZ. All right. So all right, and now y is measured from the centroid. Okay, so so it's not so the centroid is at 1.5 inches. So from the base. So if we so if we look at our cross-sectional area, all right, we get the largest y would be on the top surface would be 2.5 inches, and then the smallest y would be minus 1.5 inches for the base. Okay, so so what we end up getting here is we're going to get IZ is a constant, so it's 8.667 times 10 to the minus fourth. The moment is 10 kip inches. That was given to us. And then y will vary between negative 1.5 and 2.5. Okay, so so our equivalent stress within this section will give us at when y is 2.5, when y is 0.5, and y is negative 1.5 inches, we will get the following values of stress. We get minus 2885 psi, we would get minus 577 psi, and we would get 1731 psi. Okay. All right. So, all right. And then the last part of the problem deals with so this is the stress for the equivalent section. However, we know that the stress within the stiffer material is actually higher than the So the stiffness within the steel section is actually higher than the stiffness within the equivalent section. Um, so what we need to do is we need to determine what the stress within the composite section is. So the stress within the composite section, so this is in the steel section, is going to be equal to the ratio of the first material of the steel over the aluminum times the stress within the equivalent section. All right, so the E2 over E1 is 30 mPSI over 10 mPSI times our equivalent stress. All right, so it's just going to be 3 times our equivalent stress. So what this ends up giving us is that our stress within our composite section at Y is equal to 0.5 inches and Y is equal to minus 1.5 inches are actually going to be minus 1731 psi and 3 times 1731 is going to be 5193 psi. Okay. So what our stress distribution looks like, if we plot our stress, this is our y-axis, and then we plot our stress here. So let's say this is minus 1.5 inches, and this is positive 2.5 inches. What we end up getting is our stress is at minus 2885 psi here, and then it goes down to around 577 psi, minus 577 psi, and then once we get to sorry, this should be at this point here. This should be a straight line. Alright, and once we get to this point here where we cross over into the steel, the stress would, in theory, jump to minus 1731 psi, and then it would remain linear until it got to the minus 1.5 inches where it would get to 5793 psi. Okay, so this is our stress on the x-axis here. Okay, so that's the so that's how the stress distribution will work. As you can see in the composite section, the stiffer material is going to have the higher stress. Will have the higher stress from the material, but allows for improved strength with reduced weight overall.